Unit 6, page 192 to 194, Properties of Definite Integrals. Given the integral statements, write what you think each is equivalent to. Okay, so because we're doing this in video note form and not in full class, we're actually just going to go through this in the video, and I'll explain as I go. So for the first statement, we have the integral from a to a of f of x dx. That's going to actually equal 0. And that's because if we use FATOC, that means that the integral from a to a of f of x is equal to capital F of a minus capital F of a. Right, so that's using fundamental theorem of calculus. Given that a is less than c, which is less than b, the integral from a to b of f of x dx is equal to something. So let's sketch a graph of a function, and we have a, b, and c is going to be in between. So if we want the area from a to b, we can split that to the area from a to c plus the area from c to b. So this is going to be equal to integral from a to c of f of x dx plus the integral from c to b of f of x dx. Remembering that when we write the integral, the number on the bottom should be less than the number on the top. So if we have the integral from a to b of f of x dx and it equals k, then when we flip our integrals, so now instead of from a to b, we're from b to a of f of x dx, then that should equal negative k. Okay, so if we flip our integral, then our answer will be negative, or the opposite sign. Given that b is less than a, then the integral from a to b of f of x dx is equal to, so if we're saying b is now less than a, right? If we want to write the integral so that we're always having the lesser number on the bottom, then we would have to flip this integral sign. And when we flip that integral sign, remembering that our answer is now going to change signs, that means that our integral is now negative. So if the upper level of integration is less than the lower level of integration on our integral sign, then we can flip it and just make it negative. We'll do a few examples of this. If k is a constant, then the integral from a to b of k times f of x dx is equal to, you can bring that k right out, which we have been practicing, and we have k times the integral of f of x dx from a to b. Another one that we've been practicing is if we have the integral from a to b of f of x plus g of x, or f of x minus g of x dx, that's equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. All right, 7 and 8 help to be a little bit more visual. So if we have an even function, which means that we have a y-axis symmetry, and we are looking for the integral from negative a to a of f of x dx. So let's say this is negative a, and this is a. They're the same number, just opposite signs. Okay, so if they're the same number, opposite signs, we want the area under the curve of those. So using FATOC, we know that means that we want capital F of A minus capital F of little a, right? However, we also learned something in this with number 2, also called the transitive property, right? This is just a regular transitive property from Algebra 1 or even prior to that, right? So if we know that 0 is going to be right in the middle of this, we can go from negative a to 0 of f of x dx and add to that from 0 to a of f of x dx. Okay, and since this is an even function, the area here is equal to the area here. So we know that the integral from negative a to 0 of f of x dx is equal to the area from 0 to a of f of x dx. So knowing that they're equal to each other and we're going to add them together, these two pieces of information tell me that my answer is either going to be 2, 0 to a of f of x dx, or 2 from negative a to 0 of f of x dx, because they're going to be the same and we're going to just have 2 of them. Okay, so you can either use 2 of the positive ends or 2 of the left side end. Now if we have an odd function where the first quadrant and the third quadrant are the same and kind of rotated, then we have, if we're going from negative a to a, these areas are now going to be the same, except one is negative and one is positive due to the position of the function according to the x-axis, right? So again, with the transitive properties, we can do the integral from 0 to a of f of x dx, and that's the positive end is going to be equal to a negative 0 to a f of x dx. Or actually, let me rewrite that. It should be negative a to 0 is equal to a negative 0 to a. Right, so then when we're using this transitive property, we want negative a to 0 of f of x dx plus 0 to a of f of x dx. And we know that negative a to 0 of f of x dx is the same as negative 0 to a. So this is negative 0 to a plus positive 0 to a, which is 0. So if we have an odd function and we're looking for the integral from a negative a to a positive a, our answer is just going to be 0 because these areas are the same but opposite signs. So when we add them together, they will cancel each other out. So now let's use some of these properties. So if we know that the integral from 0 to 3 of f of x dx is equal to 6, and we know that the integral from 3 to 7 of f of x dx is equal to negative 8, we want to determine the value of each of the integrals using the properties of definite integrals. All right, And we're going to explain by showing our work. So if we want the integral from 3 to 0 of f of x dx, we don't have that as an option. However, we do have 0 to 3. So we know that if we just switch the limits of integration, we should get from 0 to 3 f of x dx. It will be negative. So this should be equal to negative 6. Now from 0 to 7, we also don't have an integral from 0 to 7, but we do have 0 to 3 and 3 to 7. So by the transitive property, by putting them together, we should get the integral from 0 to 7. So this is equal to integral from 0 to 3 f of x dx plus the integral from 3 to 7 of f of x dx, which is equal to 6 plus negative 8, which is negative 2. Now we have the integral from 3 to 3 of f of x dx. Using FATOC, we know that means that I want capital F of 3 minus capital F of 3, which is equal to 0. Now for the integral from 7 to 3 of 3 f of x dx. So since this has switched my limits of integration, we're going to rewrite it as a negative 3 to 7, 3 of f of x dx. And then since we have a constant here, we can pull that out. So that'll be negative 3 times the integral from 3 to 7 of f of x dx. So we'll have negative 3 times negative 8, which is equal to positive 24. We're just going to do all of these problems together. The next problem, we want the integral from 3 to 7 of 2 plus 3 f of x dx. So again, we've done problems similar to this before. We're going to separate this integral. So we want the integral from 3 to 7 of 2 dx plus the integral from 3 to 7 of 3 f of x dx. So when we integrate 2, right, polynomial-like function, so add 1 to the exponent, divide my coefficient by my new exponent, and I want that integrated from 3 to 7. And I'm going to add to that, I have a constant here that I can pull out, and I'm going to integrate f of x from 3 to 7. So we'll have 2x from 3 to 7 plus 3 times negative 8. And here we're going to use FATOC. So we need 2 times 7 minus 2 times 3 plus 3 times negative 8, which will give us, in the end, negative 16. So for this piece, we have an even function, which means that I can split this into the integral from negative 3 to 0 or the integral from 0 to 3. Since we have the integral from 0 to 3, that's what I'm going to use. So this is going to be rewritten as the integral from 0 to 3 of f of x dx. And since it's an even function, I know I have to multiply it by 2. So this is going to be equal to 2 times 6, which is 12. In the final problem on this page, we're dealing with an odd function. So again, I can split this into -3 to 0 or 0 to 3, but it doesn't make a difference because if it's an odd function, that means that the integral from -3 to 3 f of x dx using transitive property equal to 0. All right. On this last page, we have a graph of a continuous function f of x, and we're going to find the integral for various limits of integration. So remembering back to when we first started integrals, integrals are the area under the curve, right? So we're going to use this graph to identify the area under the curve by using geometric shapes that we already know how to find the area for. So first area we're going to find is from 0 to 3. So we would need to know the area of this space here. It seems to be a quarter of a circle and a trapezoid, or you could look at it as a square, a rectangle, and a triangle. Right? So if we look at this closely, we have the area of this quarter circle. So the area of this quarter circle, we'll be using the function, the equation 1/4 pi r squared. The area of this rectangle, we'll be using the formula base times height. And the area of this triangle, we'll be using the formula 1/2 base times height. So to find the area of this, we have 1/4 pi, and the radius seems to be 2, right? Because we go 2 here, 2 here. So we have pi 2 squared plus the area of this rectangle, so 2 times 1, plus the area of this triangle, which is 1/2, 1 times 1. So here we have 2 squared, which is 4. A quarter of 4 is just 1, so we have pi plus 2 plus 1/2. So we have pi plus 5/2, which you could do out if you want to, but you don't need to. Now the next piece is the value from 0 to 4. So from 0 to 4, now we're adding this triangle. And if you look closely, these two triangles are the same size. So they'll actually negate each other. So when we're looking for the area, we're actually just paying attention to the area of the quarter circle and the area of the rectangle. So we just need the 1/4 pi 2 squared plus the 2 times 1, which will give me pi plus 2. Now this next piece, we want the value of the integral from -3 to 3 of f of x dx. So here we're looking -3 to 3. If we look at this function, this is an even function, right? Because if you look at the right side of the y-axis and the left side of the y-axis, they are the exact same function, just reflected over the y-axis. So because this is an even function, I know that to find this, all I need to do is take 2 times the integral from 0 to 3 of f of x dx. Now I already know what the integral from 0 to 3 of f of x dx is. I found it in my first box. So I'm going to take 2 and I'm going to multiply by pi plus 5/2. now have 2 pi plus 5. All right. Now these next couple problems are going to give you some information, and you have to use that information to identify various integrals. So we know that if capital F of 0 equals 5, what is the value of capital F of 3, where f is the antiderivative of f of x? Okay, so since it gives us these x values 0 to 3, that means that we're looking for the integral from 0 to 3 of f of x dx. And using photoc, we know that means that we're going to take f of 3 minus f of 0. So we know what this is. This is pi is 5 over 2. We don't know what f of 3 is. That's what we're looking for. But we do know f of 0 is equal to 5. So now we're just going to solve for f of 3 using algebra. So just add 5 to both sides. So we have pi plus 5 halves plus 5 equals f of 3. And if we simplify, f of 3 is equal to pi plus 7.5. Similarly, for this very last problem, we know that f of negative 2 is equal to negative 2. We want the value of f of 2, where f is the antiderivative. So given the x-axis, the x values of negative 2 and 2, we know we need the integral from negative 2 to 2 f of x dx, which is equal to, using photoc, f of 2 minus f of negative 2. And again, we're in a situation where we have an even function, right? F of x dx is an even function. It is a reflection across the y-axis. So we can rewrite this as 2 times the integral from 0 to 2 of f of x dx. We don't know f of 2, but we do know f of negative 2, which is negative 2. So now we're going to try to find the area from 0 to 2 of our function. So from 0 to 2, the area from 0 to 2, if we look closely, is just, again, the quarter circle and the rectangle, which we found down here. So that was pi plus 2. So we know we're going to take 2 times pi plus 2, and that'll be equal to f of 2 plus 2. Negative and a negative makes a positive. So we have 2 pi plus 4. And when we do this out using algebra, subtract 2 from both sides, we get 2 pi plus 2 equals f of 2. Right, that's the end of the video.